Welcome to The Explainer. Today, we're going to dive into some really weird materials. The ones that seem to break all the rules by acting like a solid and a liquid at the exact same time. You've probably seen this before, right? This strange dual behavior isn't just a gimmick you find in a toy store. It's a fundamental property in all sorts of stuff around us, from everyday plastics to even the tissues in our own bodies. And this behavior has a name: viscoelasticity. Today, we're going to unpack what that really means and look at the clever mechanical models that scientists use to actually predict how these squishy, stretchy materials are going to behave.
All right, first things first. What exactly is viscoelasticity? Let's try to crack open this whole solid-liquid puzzle.
At its core, it's just what it sounds like. These materials are a little bit of both. When you deform them, part of that energy gets stored and then bounces back. That's the elastic, or solid-like part. But another part of that energy just dissipates. It turns into heat. That's the viscous, or fluid-like part.
So how do scientists even begin to wrap their heads around this? Well, they start with two really simple, idealized ideas: a perfect spring and something called a dashpot.
Think about it like this. The elastic component, that's our perfect spring. It represents that solid-like ability to store energy and just snap right back into shape. The viscous component, that's the dashpot. Picture a tiny hydraulic piston that resists motion and just turns that energy into heat.
And here's the real key difference. It's all about how they react over time. A spring's response is instant. Bam. And it's reversible. It always bounces back. A dashpot, though, its response is slow, it's time-dependent, and it's permanent. It doesn't bounce back. It just flows.
Okay, so we've got our two pieces, our building blocks. So what happens when we start putting them together? Well, that's when we get our first simple but surprisingly powerful mechanical models. So first up is the Maxwell model. All it is a spring and a dashpot hooked together in a line, or in series, one right after the other. Super simple.
But here's where it gets interesting. This simple little setup is really good at predicting one thing, called stress relaxation. If you stretch a rubber band and just hold it, you can feel the force you're exerting slowly decrease. That's it. But it's not so good at predicting something called creep, which is when you hang a weight on something and watch it slowly stretch out over time. It only gets half the picture right.
Okay, on to our second simple model, the Kelvin Voigt. This time, instead of putting them in a line, the spring and dashpot are arranged side by side, or in parallel. And yeah, you probably guessed it, it's the mirror image of the Maxwell model. Because they're in parallel, it's brilliant at describing creep, but it totally falls flat when it comes to stress relaxation. So again, we're only telling one half of the story. So if both of our simple models are only getting it half right, how in the world do we get the full picture for real-world materials?
Well, the answer is we've got to get more complex. Real-world materials, especially polymers, are way more nuanced than just one little spring and one little dashpot. We need something more sophisticated.
And this is how we do it. We combine multiple springs and dashpots together into more complex arrangements, like this ladder network you see here. These are what we call generalized models.
By linking a bunch of Maxwell models together in parallel, we get the generalized Maxwell model. And if we link a bunch of Kelvin Voigt units in series, we get what's called the Weichert model. These more complex structures are the absolute key. They let us accurately describe both creep and stress relaxation, giving us some incredibly powerful tools.
Okay, we've got all this theory down: springs, dashpots, complex models. But what's it actually good for? Well, how about making chicken more tender?
I'm serious. A 2021 study in the journal Foods did exactly this. There's a condition called wooden breast that can make chicken really tough and unpleasant. So researchers used these visco models to see if a special treatment could actually fix the texture. What you're looking at here is stress relaxation in action. The scientists compressed the chicken samples and then measured how that stress just faded away over time. Then they fit that data to a 5-parameter generalized Maxwell model to precisely quantify how much an ultrasound treatment was tenderizing the meat. And the results from the model told a crystal clear story. Just look at this data. After hitting it with a 600-watt ultrasound, the hardness dropped significantly. And look at the relaxation time. It also dropped from about 2.5 seconds to 1.7. That means the treated meat relaxed its stress way faster, a sure sign it had become more tender. And this chart just makes it so obvious. You can see that dramatic drop in hardness right there.
It confirms exactly what the model predicted. The ultrasound treatment was super effective.
So, think about that journey. We went from these simple, abstract ideas of springs and dashpots all the way to building complex models that can be used to literally improve the food we eat. It's a perfect example of how this kind of science can have a real, tangible impact.
So the real takeaway here is that these models aren't just for academic papers. They give engineers and scientists the tools to predict, to control, and even to design the behavior of all kinds of complex materials, from high-tech polymers all the way to our dinner.
Which really brings us to a final thought. If we can perfect the texture of chicken by modeling its squish, what else can we do? What's the next frontier for materials we can design from the ground up? What other challenges are out there just waiting for us to solve by understanding this strange, fascinating world of viscoelasticity?